So I will go ahead and turn things over to her to do some introductions. Rachel.
Thanks, Becca. And I am Rachel Sparnack, the Water Resources Specialist here at the West Virginia Water Research Institute. And just a little bit of background, all three of the presentations today are funded by the USGS, either 104B program or 104G program. And so we have three different research teams from WVU that will be giving presentations on their research. So the first one, we have Charlie Shobe, who's an assistant professor of geology here at WVU, and he's joined by two of his student researchers, Eris Mann, graduate researcher, and Corey Crowder, an undergraduate student researcher. And so I'll turn it over to you all.
Great. Thank you so much, Rachel, and everybody. We really appreciate the chance to be here. And of course, thank you for the money. That's also great. It's been really fun to do this work. We're going to talk today, we being myself, Eris, and Corey. And we've also been helped a lot by another undergraduate, Isaac Miller, and another graduate student, Nick Coliani, are going to talk today about modeling and measuring erosion in streams that might be sediment impaired, right? Or those streams in which we might care about erosion because the sediment that erosion generates is harming aquatic habitat. And this is largely a problem in our part of the world and worldwide because streams, especially headwater streams, have been straightened and dredged all over the world for flood control since the early 1800s and even before. The most famous paper on this is a little dated now. It's about 40 years old. But even at that time, folks were reporting just in the US alone that an estimated 200,000 miles of waterways have been modified in this way. I mean, that actually doesn't even include the smallest headwater streams, which are actually the most commonly modified because they're so easy to do just in your backyard with a backhoe or whatever, a hard thing to document for scientists. So substantial modifications to channels that tend to have a lot of negative habitat and environmental effects. We end up draining wetlands this way because we've lowered the water table. We reduce groundwater recharge because surface water now sits lower in the landscape. And perhaps of interest to a lot of the folks on this meeting today, this process of dredging and straightening has been documented time and time again to reduce the size, number, and species diversity of fish in streams that are modified, basically due to large-scale disturbance and habitat degradation. And this is certainly a global problem, but we can give it a very local flavor by thinking about a set of stream reaches just upstream from us on sort of our home watershed of Deckers Creek. So here we're looking at an air photo of a satellite image, I suppose, of Reedsville, West Virginia. And I've drawn in the streamline for Deckers Creek. And it may seem like I've approximated this, right? Streams don't typically look like that, but indeed these streamlines are really accurate. This is actually how the stream looked. And Deckers Creek has been subject to a number of sort of dredging and straightening campaigns over the years. We got our hands on a report from the most recent, I believe, which was 1963, run by the USDA. But we have evidence from old air photos that we've collected that there were major disturbances to this reach as early as before 1938. Those are the earliest air photos we have, and they already indicate really substantial hydrologic modification, basically with the idea of reducing flooding on the surrounding farm fields. The benefits of reducing flooding were quantified in this report, but the costs to habitat were, as usual, not quantified. So of course, you come out with the answer that you should do this dredging. Friends of Deckers Creek, the local watershed group, is doing a lot of really excellent work in this watershed. And in their most recent, or the most recent I have, watershed-based plan, they note that at least 6 miles of channel in Upper Deckers Creek were dredged and straightened as part of this most recent flood protection project. They argue, and we'll sort of test this idea throughout the talk today, that these channels are prone to presumably rapid stream bank erosion. Certainly anecdotally, we observe some evidence of that. And they draw a connection between that stream bank erosion and what they call evidence of sediment contamination. And contamination here it's not a chemical thing, it just means too much fine sediment, right? And that stuff sort of mantles the channel bed, destroys aquatic habitat, and ultimately can make for these really kind of mucky channels that we often see running through bottomlands on the Appalachian Plateau. And indeed, if we look back to our study area, we can see a little bit of evidence for bank erosion. I took this picture on an initial field trip with Rachel, actually, and we do see a small portion of the bank here that's collapsed into the channel. So there is maybe some anecdotal evidence that this is going on, but this is something that we want to be able to quantify. So I'm going to turn it over to Corey first to talk about our field work.
So yeah, so what we wanted to look at is how much the banks actually supply the sediment to the stream. And so to go about that, we've been doing repeated surveys of different cross sections along the stream. And that is myself there on the right with Isaac Miller on the left. And I'm standing behind the total station that we use. And so the way that works, just a quick overview, is we shoot a laser to hit a prism on the head of the stick that he's holding there. And that allows us to measure the distance and the elevation of any point along our cross section. And so to look at the cross sections that we have here, we have been able to set up 4 along the stream, with the lowest one on the screen being the furthest upstream and the highest being the furthest downstream. And so for time today, we're going to look at 3 of those cross sections. So getting into that, what you're looking at here is a graph showing the actual cross section that we were able to measure via surveying. And so on the x-axis, you have the cumulative distance, and that's along the stream profile. And then on the y-axis, you have the height above the thal leg, so right in the middle of the stream there. And so these are our first survey of the area, and then the most recent. And what you're looking at here is the orange is showing you the area of sediment that has been eroded away. And then the blue is the area of sediment that has been deposited on any given point. And so one thing to comment on with this method is the degree of uncertainty. And you can see that up in the top right corner there, and where those lines don't really match up the best. And so that amounts to about just a few centimeters difference. And we can account for that over the entire cross section. And then so we've also been continuously monitoring the hydrology of the channel. And so we've been able to measure about 6 floods that have reached over 1 meter, and then 1 that has reached nearly 2 meters. And so that allows us to understand the stressors on any given point there. And then so relating back to the cross section, and this is the same that you looked at before, this is all of the data that we've been able to collect for that first cross section point. And so what you can see here is there's actually fluctuations in the elevation on any given survey with not much net change over time. And so one thing to point out here is that on the 2 steps that you see around 1 and 1.5 meters, those have fluctuated over time, both eroding and catching sediment. And then we also have these here at about 1 meter, where we have bank slumps going down into the stream. And though it does look like there was some change there, the amount of sediment that's actually then deposited onto the bank is negligible when you take into account the fluctuations of the bed erosion and deposition. And then we see that across our other cross sections too. This is cross section 2. So the next downstream, and you have the same fluctuations with really minimal net change. And again, in cross section 3, the same type of shape, but again, nothing's changing over the course of the year. And then so just kind of to wrap that up, we were able, in being able to measure the hydrology, we were able to get that the depth, at that depth, there was about 20 pascals of stress exerted on the bed. However, that didn't really translate to a lot of change in the overall shape of the stream. And so that leaves us to ask, where is all this sediment coming from that's getting into this reach? And so looking at the evidence that we've collected so far, we are more so attributing that to the construction and the different projects going on in Deckers Creek and the land use. And so now I'm going to turn it over to Eris Mann to talk about the longer term impacts.
All right, thanks, Corey. So what we're seeing from Corey's research is that there's not a whole lot of degradation of the channel, at least observed right now. But what I'm looking at is more of a long-term, I guess, look at what the straightened and drenched channel might end up being. And I guess these straightened and dredged channels, they tend to, I guess, historically have had a lot of degradation eventually, and also the potential for aquatic habitat to be destroyed or hindered. So my role in this is to, so I want to look at some sort of options for mitigation intelligently. So there are some options for mitigation that maybe aren't so helpful for the aquatic environment, but there may be some that can maybe return it to its more natural state. So what I did is I used a digital elevation model to look at this. This is what we're looking at here. It's a digital representation of the topography of this study reach, and those colors, they kind of represent different elevations. And my objective is to determine the erosive stresses that are put on this through a two-dimensional hydrodynamic water flow, surface water flow model, which is called HECRAS. And also I'd like to examine possibly the influence of reconnecting some abandoned streams. So there are some abandoned streams that were more in their natural state that were excluded in this straightening and dredging. So to show you the model, this is a flood simulation with a discharge of 25 cubic meters per second. And let's see, here we go. Okay, so in the color bar over there, this shows you the shear stress that's put on the stream channel. And with a straightened stream, you have a lot deeper, straighter channels, and also you have a steeper slope consequentially. And this is causing a lot of shear stress throughout the study reach. And this is potential, we're not seeing it in Corey's study, but this is all, relatively accurate potentials for shear stress. So we're seeing high flow velocities, which increase the shear stress. We're seeing up to 18, possibly 20 pascals of shear stress, which is pretty high, and an overall potential for degradation of the stream. And again, I say potential, more of a longer time scale. In going over this, I did notice that there are some meander scars, which is a remnant of what the stream was in its more natural state. So you can see these kind of squiggly lines here. That's more of a sinuosity that you would see in a natural form. Using that information, I was able to manipulate the DEM into something that would have been before the last straightening and dredging. They've had many different iterations of this. So I did my best to kind of to turn the straightening and dredged channel into a more meandering, more natural form. And that's what you see on the right panel here. And after running the model for the, here we go. So we're running the model for the manipulated DEM, where it has more meanders within it. And it's the same flow velocity, same discharge, 25 cubic meters per second. You're still seeing a lot of reds and yellows, and that's because we're still seeing a lot of straight streams in this last iteration. But if you look at the northern reach of it, where I pointed out those meander scars, it goes down quite a bit. We're seeing 0 to 3.6 pascals rather than 14 to 18. So it's quite a bit of difference there. And in that you're seeing a lot slower flow through these and a lot less of a slope in these meander scars. So on the left panel, just to kind of compare the two reconnecting streams on the right side, you can see that reconnecting to the meander scars can drastically reduce the shear stress potential when compared to the current state that it's in right now, the straightened state. It's a lot of reds and yellows. So just to kind of recap on this, we're seeing a lot more stress in the straightened stream, and erosive stresses can be reduced by restoring it to its sinuosity, its more natural state. So reconnecting the current stream into these meander scars, not only it improves the stream quality and aquatic habitat, but also it can reduce a lot of shear stress and potential for erosion. It is also could be a lot cheaper for a remediation plan. So reconnecting these abandoned channels, that's more promising to bring it more to a natural state. And also this software is free. So it's something I can do for free, and it doesn't cost anything to run these models. Before dumping a whole bunch of money into a remediation plan, we can run these models. But I'll turn it back to Charlie.
Excellent. Well, thank you guys both so much. Just to kind of wrap that thought up, we sort of have two conclusions to send you home with. The first is that probably as an overall source of sediment contamination in the stream, bank erosion is not our biggest problem and not the place to put our money. And I would extend that to basically all Appalachian Plateau streams and potentially others around the world. However, we do know that over longer timescales, it is the sort of enhanced erosion that is governing some issues that we're seeing, some channel widening and things like that. And if we want to find solutions to that, there is potential in these sort of abandoned channel reaches that were orphaned when these straightened channels were cut. And here you can see Corey and Isaac kind of sinking deep into one of those. And that's one place where there's potential for cheap restoration that takes advantage of those. So please contact us at the address below with any questions, and thank you very much.
Thank you all. Those were really great presentations. Do we have any questions for the group? Well, I do have a question. So you're able to run the flood simulation for free. Would you need to go into the field and sort of ground truth that with some field studies? Say there's a watershed group in another area that has a channel that they're interested in doing stream restoration work because they think there's erosion and sedimentation. Could you possibly do stake measurements to see if there's movement from stakes to ground truth that?
Yeah, that's an excellent question. You definitely would want to do some ground truthing, right? Because there are two sides to this. There's where are the erosive stresses and where is the channel material most susceptible to erosion, right? So there's the driving forces, but the resisting forces, which we didn't discuss here. We are at our study site on Deckers measuring those resisting forces. So not only do we have erosion pins in like rebar stakes, like you're describing, but we also actually, in this picture, Eris is using a geotechnical technique to measure the shear strength of the soil, which is a imperfect, but about the best we have proxy for how effectively it resists erosion by flowing water. And so you definitely want to kind of calibrate these models to a given study site, but that's a relatively easy thing to do. You need to know some things about kind of the vegetation and surface roughness in the area. And then it's really about getting some sense for those resisting forces. And the beauty of these models really is that it allows hypothesis testing over space and time scales that we just don't have the resources to measure.
Okay, we had another question pop up in the chat from Martin. About 15 years ago-ish, there was a practice or policy of mowing down the vegetation along the straightened channels. Is that a bad idea?
Yes, it's a bad idea for a couple of reasons. That's an excellent question. Two reasons that's a bad idea that immediately come to mind, though I'm sure there are also some more ecologically oriented reasons why it's a bad idea. One is that vegetation provides flow resistance, right? So we see in a lot of these more enlightened nature-based restoration strategies, people actually trying to plant native shrubs and other things that impart a lot of flow resistance, meaning they slow floodwaters down and reduce the shear stress the bed experiences for a given flood magnitude. So if we take that flow resistance away, we get a lot higher shear stresses on the channel bed. And it's also a bad idea because anything that inhibits the health of vegetation is going to inhibit the development of basically root masses that help stabilize the channel bed and banks. Excellent question.
And Martin also asked if you could repeat your conclusion. Bank erosion is not a problem across the Appalachian Plateau.
So no, I want to be really clear about this because I understand why in those words it would sound counterintuitive. I think that in this landscape, bank erosion is not one of the chief contributors to sediment contamination, meaning that bank erosion is not one of the chief components of the annual sediment budget of this watershed. That's what I'm saying. That does not mean that we're not experiencing over long timescales bank erosion that's doing other things we don't like. I just think that in light of a rapidly urbanizing or suburbanizing watershed, given the field data we've collected, it's unlikely that sediment sourced from that bank erosion process is one of the major contributors to sediment impairment. But that doesn't mean we don't want to mitigate bank erosion for other reasons, which is why we're sort of going down this line of inquiry with Eris's work. That's a great question. Thanks for giving me the chance to clear that up.
All right. Well, thank you all. I know that, Charlie, you have to run and teach class, so we'll let you go. Thank you for taking the time.
Great. Thanks very much. And I know it's really rude to run. I wouldn't if I weren't teaching. So thanks, everybody.
Thank you.
Thank you. All right. And so the next presentation will be given by Erin Shepta. She's a student here at a PhD student here at WVU under the direction of Brent Murray, an assistant professor of aquatic ecology. And he's not able to join us because he is also teaching class. So Erin, I will hand it over to you.
Sorry, give me 1 second here.
No problem.
All right, perfect. Can everybody see the presentation already?
Yep.
All right. So hi, happy Groundhog Day. My name is Erin Shepta, and as mentioned, I'm a PhD student in the Davis College of Natural Resources. And today I'm going to be talking about a project that we are currently working on surrounding the evaluation of potential factors that might be limiting the expansion of the invasive Asian carp. So just a quick background on the Asian carp invasion for those who are not familiar with it. Asian carp refers to 4 different species of carp, including the grass carp, our black carp, our bighead, and our silver carp. All 4 species were first introduced into the lower Mississippi River Basin between the 60s and 70s and have since really expanded throughout that basin. While all 4 have been shown to have devastating ecological impacts, the main concern currently is with the bighead carp and the silver carp, shown here. They are planktivores, so they consume large amounts of plankton that are required for our native fish, especially in their larval stages, and our native mussels. So, as I mentioned, these fish were first introduced in the lower Mississippi, shown here, and have since expanded upstream into the Mississippi's major tributaries. Once they reached the upper Mississippi here, their populations took off very rapidly and they spread throughout the system very quickly. However, when they reached the Ohio River, another major tributary, their spread kind of stalled or slowed down. And the question then became why? What is it about this Ohio River and its major tributaries, the Tennessee and Cumberland rivers, that are slowing these species spread? If we can identify these, we can potentially use them to try and slow its spread in other basins. We think it has to do with some kind of environmental factors, biotic interactions, or some combination of the 2. So to explain what I mean by spread, it's important to understand the process by which an invasive species invades an ecosystem. So originally, a species just exists in its native population, shown here, and then a couple individuals from that population are transported through some kind of vector and dispersed into a non-native ecosystem, and this is known as the dispersal phase. Those individuals that have been dispersed then start reproducing, their population starts to grow, and they're in the establishment phase. So they establish this founder population shown here. Spread, which is what we're looking at here, is a coupling of that dispersal throughout the ecosystem and establishing these different populations. So there are many factors that we know regulate the speed of spread across a landscape. But for this project, we were mainly are focusing on environmental heterogeneity of this system, the establishment and recruitment success of these Asian carp, and potential biotic interactions that they're having, such as competition, that may be slowing their spread. So I'm going to go over all three of these projects very briefly and what we are currently working on. So I want to start with that environmental heterogeneity project. The question here is, are biotic conditions varying between and among those focal watersheds and thus influencing that rate of spread? So we have the upper Mississippi where the fish are doing really well. And then we have the Ohio and its major tributaries, the Tennessee and Cumberland, where they're really not doing as well. So the idea here is we want to collect long-term existing data sets on local abiotic conditions. We want to be able to identify the key environmental differences that exist between these basins and eventually be able to incorporate information on our carp to try and see if those differences are influencing the probability that they are there. So we don't only want to look at differences between those basins, it's also important for us to look at differences within each of these focal basins as well. So we split each river up into something that's known as invasion fronts. So here I have an example river shown with the Ohio, and these squares represent the locks and dams. So starting downstream in this red, in your Camelton Lock and Dam, the fish are established. We have a high abundance of carp and they're reproducing pretty rapidly. Once we reach upstream in this invasion front, starting at Markland, we see still a pretty moderately high abundance of carp, but there's not a lot of evidence that they are reproducing. And moving then upstream even more at Greenup Lock and Dam, we have a couple fish present, but we don't have any evidence that they are reproducing or establishing those populations. And then upstream of Willow Island, we have no evidence that the carp are there at all. So in the framework of this invasion front per basin, we want to be able to collect environmental data across each of these fronts to try and understand those key environmental differences. We're going to use existing long-term data sets from various collaborators and websites that we can find. And we are also hoping to find daily flow data, as we believe that hydrology is a very key characteristic to influence their populations. And we're going to be putting our daily flow data into this IHA model, which is done by the Nature Conservancy, to just give us additional parameters surrounding the river hydrology. So the goal here is to organize this kind of site by each front and each basin. The goal is to do some kind of multivariate ordination analysis. So an example of what this is going to look like is shown here. For those of you that are unfamiliar with multivariate ordination analysis, what this does is takes very complex multivariate data and squishes them down into a two-dimensional space so we can better understand trends in that data. So here, dots that are closer together represent sites that are more environmentally similar than those that are far apart. So what we would hope to see is downstream, sites where the carp are doing very well are environmentally very similar to sites where they're doing well in the upper Mississippi. And hopefully we can identify environmental differences that exist in those sites upstream where they're really not doing as well. Once we're able to identify those environmental characteristics, we hope to use them in something called an occupancy model. So here we want to take information on carp themselves and see if those environmental differences really are influencing their presence and absence at each site. So what an occupancy model does is it takes presence and absence data of fish, and we're going to do this at 3 different life history stages, and it incorporates in that environmental data to give us information about if that's influencing, if they can exist at each site. So we'll get predictive models, kind of like the ones shown here, where let's say we have eggs and larval fish, and we can tell that their occupancy might be influenced by a river hydrology, such as max flow. More specifically, we're hoping to do something called a dynamic occupancy model, which is still in that same family of models, but here it's going to help us look at that change over time. So again, this is just a model of a river and how their spread might look, where circles represent different sites that we might sample. And green circles are unoccupied, meaning we didn't find that life class there. And red sites are occupied. So through time, as they travel up the river, we will see occupancy of each site changing. So the dynamic occupancy model is going to allow us to estimate 4 different parameters. The first being initial occupancy and detection probability. But more important for our research is we want to look at this thing called colonization probability. So this is the probability of an unoccupied site, so a green site, becoming colonized, turning red, over a certain period of time. And we can tell what environmental variables might influence this colonization probability. The second one that we can look at too is extinction probability. So this is the probability that one of those red sites might turn green, might become unoccupied over a certain period of time. And again, this will tell us which environmental characteristics might be influencing those carp populations. So the final project that we are hoping to do is investigating if any kind of biotic interactions are also helping stall their spread in the Ohio River Basin. So the main question with this project is, are food web dynamics, a niche overlap, really offering some kind of resistance to the spread of these Asian carp? So we're going to be investigating this using a stable isotope analysis. So we're using carbon and nitrogen taken from fish tissue samples. So here on the x-axis, we have carbon. Carbon is meant to reflect the basal carbon source within the community. So are these fish at the very base using things like algae or leaves or grass? Nitrogen, on the other hand, represents the vertical trophic position of these species, where something like species 1 down here might be a primary consumer. But as we increase trophic position, something like species 6 would probably be like a top predator in that ecosystem. So to better understand how biotic interactions limit spread, I have 2 model communities shown here. So let's take a look first at this community right here. We have a lot more species here. Circles are representing their isotopic niches. So what dietary resources are they using? And here we see the circles, they're tightly packed together. There's not a lot of space left in that community. So carp come in and they try to invade at those different life history stages. We see a lot of overlap in their resource utilization. So this is going to make it a lot harder for them to establish populations because they experience some kind of competitive pressure. As opposed to the second community over here, there's a couple more holes where the resources are not being utilized by those native species. So if carp are able to come in and fill those holes, they're not going to be experiencing that competitive pressure. It's going to be a lot easier for them to establish populations. It's our intention to look at these kind of dynamics across each of those fronts that I had discussed earlier, where again, downstream in this red establishment front, the carp are doing very well. And as we move upstream, they're not doing as well. So we're trying to investigate if these communities are saturated, if we're lacking those holes upstream where carp could take advantage. So it's becoming harder for them to establish populations. So again, what we are hoping to see is potentially in downstream where they're doing very well, the carp are existing almost in these holes in these communities. As opposed we move upstream, the communities might become slightly more saturated. The carp's niches might be overlapping a little bit more, and this is going to make it a lot harder for them to be establishing successful populations. And we want to use our uninvaded upstream community as kind of our control. It's our representation of what a natural community in the Ohio might look like. So we can investigate the mechanism of establishment by seeing if those holes are present naturally, or if they happen because the carp outcompeted the native species where they're present. So looking into the future with this project, we have 3 main sub-projects and goals. The first of which, as I mentioned, we want to understand key environmental differences that exist between places where carp are doing really well versus places where they're not doing as well. We want to use dynamic occupancy modeling to investigate if those environmental factors are influencing carp presence at all those different age classes. And last, we're hoping to use a stabilized stope analysis to better investigate those biotic interactions throughout the system. So this project is still very, very young. We're just starting out, but this is what we are planning on doing. So thank you for your time. And if you have any questions, feel free to ask.
Great job, Erin. Thank you so much. And if you do have questions, feel free to unmute yourself. All right, well, if you think of anything, you can certainly put it in the chat and possibly Erin can get to it at the end. But for now, we'll turn it over to our next and final speaker, Joseph Molina. He is a graduate student researcher under the direction of Carol Orantes, Assistant Professor of Wildlife and Fisheries.
Okay, are you guys seeing my presentation?
We are seeing it, but you need to press play so that we're seeing it in full screen. If you go, yep, and you are a little bit quiet coming through on the audio. So if you maybe get closer,
How's that?
it's a little bit better.
Yeah, still pretty quiet.
Is that better?
It's a little bit quiet, but
Let me see if I can go into my settings really fast.
okay. Yeah, it is a little bit difficult to hear you.
How about now?
That's better for me. I also turned up my volume, so I think, you know, it's coming through clear, just a little bit quiet. So we'll just have to turn up our volumes.
Okay,
Yeah.
let's go with that.
Thank you.
Alrighty, so as Rachel said, I am a master's student at West Virginia University. I work with Carol Orantes. And on behalf of this research group, which is part of our River Initiative at West Virginia, I'm going to be talking about our project, which is integrating data sets to understand climate change vulnerabilities within our watersheds here in West Virginia. So what we mean by data integration is a statistical modeling approach that incorporates multiple data sources. These multiple data sources are generally independent, meaning that they come from different agencies or organizations. And they usually have different scopes for what they want to collect, but depending on how another user might see that data, they can be useful for a singular project. And when we think about macro systems ecology or ecology on a regional or continental scale, data integration becomes very pertinent because it helps us understand processes on spatial and temporal scales. So for our project specifically, our idea was to use NatureServe's Climate Change Vulnerability Index and incorporate fish distributions from the Department of Environmental Protection here in West Virginia, as well as crayfish distributions from the Department of Natural Resources. And combining this with regional climate projections for West Virginia from Climate Wizard, we would get species vulnerability scores, which we can then combine with two independent habitat indices for vulnerability toward climate change. And when we combine this, we get this watershed vulnerability index. And so with that watershed vulnerability index, we're kind of working toward our goal here to deliver a decision support tool, which integrates climate change dynamics into aquatic management decisions. A lot of times when we think about conservation, there's usually a decision support tool. And the more informed that decision support tool is, the better results we're going to get for our conservation and the better use of our conservation dollars we'll have. So objectively, what this looks like is assessing vulnerability for West Virginia species, developing a community vulnerability index from these species. So per watershed, what does our overall crayfish and fish community look like in terms of vulnerability? Then on the side of that, we would synthesize 2 habitat vulnerability assessments. One is broad scale and one is fine scale, and then ultimately combining this for our watershed assessment. And throughout this presentation today, we're going to be following this model because there are quite a few moving parts. So I think this is going to be helpful for us to stay on track to see where we have been and where we're going. So to start out, we're going to go through some species vulnerability assessments and what that looks like through NatureServe's Climate Change Vulnerability Index. Themes and concepts that are important to keep in mind for this Climate Change Vulnerability Index is what is vulnerability, essentially, and that's the risk of species and habitat loss. And we can divide this more so into exposure and sensitivity. So how is a species and habitat enduring a threat against it? What does that intensity look like? So think about temperature changes and precipitation changes, things related to the actual climate variables. Then we can think about sensitivity as well, which is that individual species or habitat, its ability to withstand those climate threats. What is the life history of that species or habitat, and how can it endure climate threats because of its life history? Now, the NatureServe Climate Change Vulnerability Index takes in that exposure and sensitivity, provides a vulnerability score, and then when that's compounded with any documented or modeled response to climate change that exists in the literature or through research, it gives us this vulnerability index score. And so sensitivity is derived from either expert opinion or literature, whereas exposure is more so quantitative in the quantitative nature, which we can see here on the right in this map. We have a change in temperature for West Virginia, as well as a Allegheny crayfish's distribution collected from the DNR, overlaid with this in our watershed, Huckade scale watershed map of West Virginia. And so then these two things combine to give us these results of our species vulnerability assessments. So far we have 56 crayfish and fishes combined. The majority of these species are less vulnerable or highly vulnerable. So results-wise, we're seeing some polarity of either being highly vulnerable or less vulnerable. Moderately and extremely are our lowest values, which is an interesting result. That scale is something we want to look at. And right now we're in the quality control process. So we're going to be meeting with some experts on these individual species to go through our assessments and make sure that we're not missing anything. However, our scores were generated with moderate to very high confidence, but given the subjective nature of NatureServe's Climate Change Vulnerability Index, it's still important that we meet with these experts for the individual species and go through these assessments again. Looking at habitat vulnerability, we used the Manomet Habitat Vulnerability Index, which was for the Northeast. However, it did include West Virginia for 5 habitats. These are broad scale habitats. And to summarize them, we took a weighted average and the weight coming from the proportion of each habitat represented within the Huckade scale watershed. And we talked about a fine scale habitat index, which was from the National Fish Habitat Partnership. This was for fish habitat, however, that still applies to aquatic habitats. And this was more of an anthropogenic focused index. And 26 anthropogenic variables were included with these models. Things like land use and development, agricultural impact on individual creeks, streams, rivers, etc. It does exclude the climate-related impact, which is why we found it pertinent to include Manomet as a broad scale and then compound these two things. But for this index, we just averaged them across each watershed because it was fine scale. Every portion of each watershed was included within this index. Now, to combine these, we used an analysis a la Bailey-Opp and Bergio. This is what's called a star plot area analysis. And so we have our National Fish Habitat Partnership index, our Manomet index, and then we included two environmental variables or climate change related variables, which was precipitation and temperature. And then we use this area as our integrated metric. And so essentially what we're saying here is our risk of habitat due to humans. Here's our risk of habitat due to how we understand our habitats to withstand climate change. Now here are the climate change variables. What does that look like on a scored scale? And then this was normalized between 0 and 1 to give us a similar score to our species vulnerability. Now, going back to the species vulnerability, we needed to build a community vulnerability index. And to do that, we essentially took the product of the number of species per vulnerability category. So there's 4 categories, 1 being less vulnerable and 4 being extremely vulnerable. And then we multiplied that by the vulnerability weight. And so that weight was determined by which category it was. So again, 1 being less vulnerable and 4 being extremely vulnerable. So that gave us our watershed community. And then to tie this all together, we have our watershed-based aquatic fauna ecological risk index, or briefly our watershed model. And so then this was just an average of our habitat vulnerability and our community vulnerability, normalized between 0 and 1, 0 being our least vulnerable habitat or watersheds, and 1 being extremely vulnerable watersheds. So far, we have 31 watersheds assessed at the Huck 8 scale. The 32nd watershed was unassessed currently just because of data limitations, but these scores range from 0 to 0.69, and the average score being 0.22. So on average, we're looking at our watersheds being less vulnerable to moderately vulnerable, and at the highest, we're looking at critically vulnerable, which I believe, off the top of my head, that's the Little Kanawha watershed that is critically vulnerable here. But this watershed model becomes pretty important when we want to determine the where and how of management and where we put our conservation dollars, which watersheds are at the most risk, and where do we need to put the most effort. And so when we think about decision support tools, I think that our framework here shows that incorporating species and community and habitat vulnerability can really provide holistic assessments of watershed vulnerability. We can think about things such as land value, which land is more valuable to us in terms of conservation. When we look back at that map, we can see that the watersheds extend past West Virginia's political boundaries, and then we can start to build periphery watershed partnerships with other states and organizations if those watersheds are in need of such conservation. And then we can break this up into species, community, and habitat vulnerability individually. We can start to understand which is driving the vulnerability of a watershed so that we can put the effort into either one of these things or all of them, depending on the factors that are affecting it the most. And with that, I'd just like to acknowledge the Water Research Institute for the funding and support, as well as the DEP and the DNR for their support and continued support on this project. And any questions, I will start to take now.
Thank you, Joseph. Again, feel free to unmute yourself or put it in the chat. So we do have something going on in the chat related to Aaron's presentation. And so Martin asked, do the guys who have boated every week on the rivers have a gut call why carp are moving up more slowly? did the 2 recent HAB blooms have an effect? And HAB would be harmful algal bloom.
Oh, is it, do you want me to answer like out loud or, okay, because I wasn't sure if I wanted to put it in the chat. I didn't want to steal Joe's thunder. Good presentation though, good, great job. Yeah, I mean, I've talked to a lot of different people that have been working on this basin far longer than I have, for sure. I haven't heard anybody talking about any kind of harmful algal bloom influencing the presence or absence of bighead or silver carp in the Ohio. I have heard a lot of different gut calls on different age classes. A lot of the times people in the Ohio seem to think it is the establishment success. It's that the juvenile fish don't really have the habitat they need to develop, and it has potentially something to do with their reproduction. I don't know that it's necessarily influencing their adult life history stage. But hopefully we can check that out with this project.
Thanks, Erin. Any other questions for Joseph or Erin? All right, well, I will let Becca wrap things up.
Yes, so first off, let's give a hand to our presenters today. They did a wonderful job and I learned a lot. I hope everyone else did this wonderful Groundhog's Day. We will be sending out a recording and a link to any presentations from our presenters. I'll email each of you if you haven't already sent me your presentation about getting that so we can put it on our website and people can, keep learning even after today. So thank you again and hope everyone has a wonderful day today.